Hello, everyone. My name is Shengyi, and today I'm glad to introduce our work, Normalization by Evaluation for Non-cumulativity. And this is a joint work with Jason and my advisor, Bruno Oliveira. So the talk will be split into 5 parts, and first we will talk about background and motivation. This will also cover the high-level ideas of our work. And the next 3 sections we will develop our proofs more detailedly in 3 parts. And as a final part, we will give some conclusions and also final remarks. So without further ado, let's go into the background and motivation section. So people in this venue should be all familiar with dependent types, but still let me introduce it a bit. So in simple type systems, types and terms are separated. So types classify terms and terms perform computations. In dependent type theory, this separation becomes blurry. So types themselves can depend on terms. And then once again, we have this very classic example of dependent type systems, which we have a vector of a fixed length, and this length can be included in this type. But we all have another question that if this, with this blurred separation, what are the type of types? Or in our terminology, we call it set. So set, if we give set to set itself, then it leads to Girard paradox, which breaks the consistency of this type theory, and we can now use this type theory as a basic or foundation of a proof system. So that's definitely not something we want. And one solution is that we stratify types into universes. For example, in this case, we have natural numbers living in the zeros universe, and the zeros universe living in the first universe, and so on. This kind of stratification prevents self-reference and paradoxes. And with universe, we have different ways to design universe hierarchy. So suppose we have this natural numbers lives in the zeros universe, and this is the traditional cumulative rule, which says every type lives in the smaller universe also lives in the higher universe, which means T lives in the set I, also a type, T is also a type in the set 1 plus I. And you can apply this rule multiple times so that you can lift types to any arbitrary higher universes. In rock, cumulativity is enabled by default. So if you have a type in universe I, it's by default, you regard it as a type at the universe J if I is smaller than J. So in Agda, things are a bit different. The non-cumulativity, which is the absence of the cumulative rule, is enabled by default. So you cannot write this function because A only lives in the set L, but not set L. So Agda, in its standard library, it provides a manual adjustment, so you can lift a type to a higher universe by this lift in the Agda stdlib. In general, these 2 kinds of universe hierarchy have their own pros. So for non-cumulativity, usually you enjoy typing uniqueness, which means any typable terms are given a unique type up to equivalence. And also it induces simpler constraint solving if you have universe polymorphism, because all you need to do is to use unification to solve the universe level. With cumulativity, people can also argue that it gives a more intuitive set theoretic explanation, and it increases the expressiveness of this type system. The cumulative rule not only differ in this, but if we think about their typing rules, these design choices also influence other typing rules. For example, in the cumulative setting, the pi formation rule, for both domain and codomain types, they can reuse the existing universe level. But in the non-cumulative setting, we have more precise universe level control, which the pi type lives in the max JK universe level of its domain and codomain type. We can also abstract over Agda's manual universe level manipulation rules into these 3 following rules, which we have a lift type constructor with also its introduction and elimination forms. But for a dependent type system to really work, we usually want some computation on types. For example, we want this f can be applied to this variable x, even though their types doesn't match exactly. So it means our type checking or the type theory must consider some equivalence relation. A reasonable equivalence relation is a definitional equality, which can be viewed as a reflexive, symmetric, and transitive closure of beta or sometimes eta equality. And we want our normalization or type checking or the conversion checking algorithm to enjoy the following 2 properties. The first being soundness, that says it normalizes a term to an equivalent term. And second is a completeness, that given 2 equivalent terms by this equivalence relation, our normalization algorithm gives the same syntactic normal form. Normalization by evaluation is a widely used technique to achieve normalization. It's a method of obtaining the normal form of terms by appealing to their denotational semantics. a term is first interpreted into a denotational model, and then a canonical, some mostly beta normal and eta norm representative is extracted by reifying from this denotation. In particular, in our talk, we are interested in untyped normalization by evaluation studied by Andreas Abel in his thesis and a lot of following work. It has the following 4 characteristics. It adopts an untyped domain model, and it uses the Brown level representation, or sometimes known as the locally nameless in this setting, so that the names remain stable. And third, it also adopts explicit substitution, which helps to justify the algorithm behavior on the beta equal terms. Lastly, it uses a delayed eta expansion, which behaves very well, that it can normalize a term to its eta law normal forms for a lot of eta extensionality laws. So these are the 3 advantages. We also introduced the first one. And lastly, but also importantly, that Abel's untyped NBE has a very direct correspondence to a real implementation. And it also easily mechanizable. So it's maybe as far as I know, it's only one of the few mechanizable NBE algorithms that scale well to dependent type systems. However, in previous works, their correctness proof heavily relies on the cumulativity structure. Because in Abel's original proof, they use this limit-taking operation on natural numbers so that their further proof is fully oblivious to the concrete universe levels. Here, we can see it takes the universe, it takes a limit on this natural number index universe to omega, so that they lift all types to this high enough universe, which is the ordinal of natural numbers, so that every types can be interpreted on this highest universe level. This is only valid for cumulative universe hierarchy. And Jason's proof, a refined Abel's proof, they use existential quantification to explicitly denote universe levels, but they still depends on the following master lemma to adjust the universe levels. We don't need to look at the signature, but the key point is here that we need to lift all types to this max ijk levels, and this ijk are given by 3 different existential quantifications. And the natural question is to ask, can we prove the correctness of NBE if we don't have the cumulative rule? And our work answers this question positively, that we provide a mechanized proof of NBE's correctness for a subset of Martin-Löf type theory with a full non-cumulative universe hierarchy. And the key idea we adopt is to precisely tracking the universe levels everywhere to get rid of the existential quantification. And we adopt this 3-step proof strategy. We first develop a fully annotated syntax and typing rules for precise tracking. And the second step, this precision is mirrored in our semantic model. So we're developing a refined semantic model which is composed of a PER model, a partial equivalence relation model, and a cryptic logical relation model to justify the soundness and completeness of our NBE algorithm. And lastly, we further show that although these annotations are technically helpful, they are logically redundant, and we can remove all these universe level annotations, and we can still have a system and an NBE algorithm that performs very well. So let's get into some nested details. So this is our syntax. So our type system include pi types, natural number types, and also the lift types and terms we introduced earlier. So we also support large elimination on natural numbers. So as we also mentioned, that Abel system took the explicit substitution approach. So we also have an explicit syntax for substitutions. And our normal forms and neutral forms are quite ordinary. The normal forms are basically introduction forms, and the neutral forms are elimination forms blocked by neutral forms, and they don't contain explicit substitutions. But the things in difference is that here, every subcomponents of our types and all context entries are additionally annotated with these universe levels. So this superscript ij all denote such annotations. And also, these are the typing and equality rules. We show just a subset of it. But it shows a formation rule of important type constructors, and also the beta rule and the eta rule of the pi types and the lift types. So we also annotate each judgment with this universe I, which is this superscript on each column. Okay. So with this help, we can also mirror this same level of precision into our semantic domain. So it's maybe a little bit contrary to what people may think of a denotational domain, that this domain we adopt, or the untyped domain adopted by Abel, is quite syntactic. So actually, Daniel Gritzer coined this as the syntactic semantic domain. And you can see that this domain only differs from the syntactic terms in 3 ways. So first, we took a closure-based semantics. And then we use de Bruin levels instead of de Bruin indices, which gives us a stable name on the context extension. And last, we have a built-in reflection and reification to mark delayed eta expansion. And also, you may notice that we also annotate these domain values with these universe levels. And this is a diagram of the NBE algorithm for this system. So we first evaluate into a semantic domain, and we perform delayed reification that gives us eta long, in some sense, eta long domain values, and then we can read it back to eta long normal form. This is just to give a concept of how this thing works, but we don't introduce this today, and the detailed concepts and definitions are in the paper. Because of our syntactic semantic domain, this evaluation and reification function are actually very straightforward. And the second step is to build the meta theory. And with the help of explicit substitutions, beta equivalent terms are evaluated to the same values. So NBE is actually complete with beta rules, but we still need to justify the eta rules. For eta rules, we need a partial equivalence relation model that it's a model on the semantic values, and we need to guarantee that related values are read back to the same eta long normal form, and the equivalent terms are evaluated to related values by this per. And this is an inductively recursively defined per for our semantic values. We also don't look at the full definition, so we need to cover all the types in this per model, because the inductive definitions is inductive on each type constructor, and this elimination form gives another per relation that for values under this type values. But we can compare with how this differ from the cumulative setting. So in the cumulative setting, we can always reuse this higher universe level I, so we don't need to keep track of which universe level each subcomponents are in. But for the non-cumulative setting, we need to reuse the information in our semantic values so that we know exactly which each subcomponents or subvalues of our type values are habited in. So we need to extract this information from this JK information from our universe level annotations. And with the help of per model, we can develop a semantic judgment, which says every 2 syntactic equivalent terms are evaluated to related values. And we can build this semantic judgment, which is called fundamental theorem completeness. And the NBE's completeness is the corollary of this fundamental theorem. And similarly, to establish soundness, we need a gluing model that glues a term with a value A. So this gluing model needs to be built on first induction on the universal level I, then on the per model we defined previously. And we have 2 mutually defined relations. One is glue a type to a type value, the other glues a term to a term value. And similarly, with this gluing model, we can develop a fundamental theorem of soundness. And similarly, the soundness of NBE is a corollary of this fundamental theorem. The details and the proof details are in our paper. And we have some interesting consequences of after we establish the soundness and completeness of our NBE. First, we have the injectivity of type constructors that says pi types are equivalent only if and only if their subcomponents are equivalent, and also the leaf types are equivalent similarly. And then we can finally establish typing uniqueness, which says any typable terms in this system can only be given equivalent types. And we also have some semantic consequences out of this NBE soundness and completeness. First, we show that our type theory is consistent, that we cannot build a term of this pi type, which is a kind of a predictive encoding of a false type under the empty context. And we also have the canonicity, which says a term of a closed term in the empty context of type nat must be constructed using our constructors. And in the last step, we show that these annotations are actually not necessary, because in our daily programming with Agda and Lean, which also adopts a non-cumulative universe hierarchy, we don't really write these annotations, and the type checker or the conversion checker operates just fine. And we show that indeed we don't need these universe annotations for this system, and we have this clean syntax again. So this is basically the same as the previous syntax, only differ in that we have no more universe level annotations. And in this section where we establish the output completeness and the syntactic equivalence between the ascribed system and the unscribed system, And using these properties marked by these solid lines, we can actually deduce these properties in dashed lines by transporting all the proofs we proved in the ascribed system to this system. So because these two systems only differ in their universe level annotations, the direct linkage to connect these two systems is just by erasing all the universe level annotations. And we show this erasure keeps all our syntactic judgment valid. So basically, one judgment hold in the ascribed system hold if and only if it holds in another system. So the completeness direction, although we show this equivalence in a symmetric way, but their proof is actually non-symmetric, especially the soundness direction is much more difficult than the completeness direction because we need to show that the re-annotation of universe levels only needs two equivalent terms. So we need a much more stronger conclusion to actually show the soundness direction. And we also can show that we have an NBA algorithm that works on this unscribed syntax directly. So this is defined in this way. And we have this, we call it output completeness that says if the ascribed MBE has an output, then this unascribed MBE also gives us the output. It's always true. This induction is actually simple because our MBE is defined in an untyped domain. So we don't need to care about its word typeness. So we just do a plain induction. We can just show this theorem. And with it, we can show that by transporting the soundness and completeness we proved before, we can then show that this unascribed MBE also works well on this unascribed syntax. So we can get rid of all the universe level annotations in the system. And now let's make some conclusions. So in summary, we proved that Alibera's untyped MBE is correct for MLTT with a non-cumulative universe hierarchy. Full definitions and proof sketch are in our paper. And all our proofs is fully mechanized in the Agda proof assistant using the induction recursion as a kind of standard extension to its meta theory. We also include a mechanization of a cumulative hierarchy, and we provide comparative analysis of how this kind of difference in the universe hierarchy makes a difference in our proof and mechanization. And there are some takeaways. So the proof relevance is hard to deal with, and rewriting in Agda is not pleasant. And the second thing is some invariance. In our example, it's a universe level invariance. It's actually well kept by the algorithm itself because it does nothing wrong with this. It does not manipulate these universe levels directly. So it should keep this as an invariance. But to really reason about this correctness, we need to take a much more effort to really reason about this correctness. And there are also some interesting questions that we leave it as a future work that could the imperative encoding of the per model instead of induction recursion encoding as we adopted in the Agda could help simplify the per definition. Actually, in a paper by McGill, they have this mecTT, which they actually mechanize the similar system in the with cumulative universe hierarchy in ROC use this imperative encoding. And the second question is this ascription that erasure strategy really necessary, or can we have a more direct proof possible? So that's all for my today's talk, and thank you, everyone.
Are there any questions? Please queue up at the microphones. I should also not stand in the way of the camera. Anyone? Thank you, Ombrish.
So do you have e-term for the unit type in your, can you support eta for unit?
I think we can support eta for unit. I think the only thing we cannot, because in Alibera's framework, I think he mentions that the eta is not a problem. The only thing I think we have problem is like a disjoint sum. So disjoint sum could be problematic, but I don't think because we use a typed MB. So we have this typed information.
Type information, yeah. And you work with an untyped model, but you still have the type information.
Yeah, we still have the type information, so it should work for the eta for unit type. Yeah.
Okay, another question. For the conversion relation of your theory, do you prove that it is a proposition? I mean, that there's only one unique way to prove conversion, or you don't need this?
We don't need, I think we don't need this. Yeah.
Okay. Thank you. Any other questions? If not, then I have one, quick one. So could you go back to your definition of pi with the levels? So the pi type.
Oh, pi
yeah, so
type.
what you do is you make I be the maximum of j and k, right?
Yeah, yeah.
Okay, but if you are the kind of person that really, really likes pre-sheaves, like I suspect the next talk, you're much more likely to have a different pi type at every universe level, and you're likely to have lifts, and then you have conversion rules saying that if you lift a pi, it becomes the pi at the next level. Would this method adapt to this?
I cannot give a definitive answer. I think potentially yes, but yeah, I cannot answer that firmly. Yeah.
Okay.
Yeah.
Interesting further research then.
Thank you. Thank you for bringing it up.
Okay, in that case, could we thank Shengyi once more, please?